Okay, so today's lesson is focusing on something that we call the ideal gas law. And the ideal gas law is a basic, a sort of a basic algebraic expression that we are going to work our way through and do a few examples of today. So let's talk about the ideal gas law for a minute. And in order to do that, we're going to talk about the four measurable quantities of a gas and how they relate to each other. So the first measurable quantity of a gas is something that we call pressure, which has which the variable is going to be P. So this is pressure. And that unit is going to be in the atmosphere or the ATM. Okay. The next variable is volume. And that unit that the value has to be measured in is liters. The next unit or measurable quantity is number of moles or amount of particles, which we will call the mole in this unit. Okay. And then lastly, the one that we talked about on Friday would have been temperature, which has to be in the Kelvin temperature scale. Now, there is I left a space on purpose here because there is a something that we need to discuss a little bit. One of the things that we need to discuss is something that we call the variable R. Now, what has happened is that when scientists made observations about what would happen about the relationship between pressure and volume, or pressure and number of particles, or pressure and temperature, or pressure, amount of particles, and temperature, whatever they were making observations about, there were some pretty obvious observations. But when you were making observations about all four of these particular variables, there was always a difference between the observation and the math that scientists did, and that difference was always roughly the same value. So, in order to make the math match the observations, scientists developed something that we call the ideal gas law constant. And that has a value of 0.0821, and its unit is ATM, liters, moles, Kelvin. That is its unit. It's not extra math, it's its actual unit. And I'm going to try to show you when we do some examples how that unit actually works. So, using these four measurable quantities and the ideal gas law constant, we can create a formula that looks something like this. Okay. So that's the formula for the ideal gas law. And I can tell you that we are not necessarily going to make you memorize the formula for the ideal gas law, or are we going to make you memorize the ideal gas law constant? We will give those things to you, but your job is to make sure that you know how to use them. So there are some examples that we're going to do. There's about 3 of them. And when we do those 3 examples, hopefully you will feel sort of confident with this particular skill. Any questions before I move on? Example number 1. I am a giant fan of taking the time to identify my variables. It helps to keep organized what I've been given and what I've used. So I usually start by taking them and writing them down the side. P, V, and then the N, and then the R, and then the T, right? Now I go ahead and I read my problem, and my problem tells me about those variables. So now I know what I have and what I'm using. So in this instance here, it says, what is the pressure? So the question is asking me to calculate the pressure. So that's what I'm going to be solving for. When you have 0.577 moles of CO2, so 0.577 moles of CO2 in a 5 or a 0.5 liter flask at a temperature of 303 Kelvin. Now, the R, or the ideal gas law constant, is not going to change. That's going to be something that you will always know. So that's going to be 0.0821. And again, our unit is ATM, liters, moles, Kelvin. So that's our unit. I'm going to try to show you how this works. The next step of this process is to write the formula and then substitute our values in. So in this process here, we have our formula, which is PV equals NRT. So I'm going to take the variables that I have values for and substitute them in this formula. We are solving for pressure, so I'm going to put that in there like a P as a P. I'm going to take 0.500 liters and substitute that for V. I'm going to take 0.577 moles, substitute that for N. I'm going to take 0.0821 ATM, liters, moles, Kelvin. And then I'm going to substitute that for R. And then I'm going to take the 303 Kelvin and substitute that for T. So now that's all that is left to do is to combine things that I can combine. And so in this case, I'm going to grab my calculator and I'm going to combine the things on the right-hand side. So I'm going to take 0.577 times 0.0821 times 303. And so what I'll be left with is this, P times 0.500 liters will equal 14.3536251. Now, in this case here, I have some things that the units that can cancel out. For example, I have moles that can cancel out, and I have Kelvin that can cancel out. So my unit that's going to be left over here is simply going to be ATM liters. Now, the next step of this problem is I'm going to divide both sides by 0.500 liters to get P by itself. So I'm going to divide both sides by 0.500 liters. And hopefully we will be able to cancel out something like liters. There it is. And now we'll be left with the unit of ATM. So if I take the 14.35 blah, 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 divided by 0.5, I get something in the ballpark of but we have to assess significant figures. So in order to do that, I'm going to go back to my original values. And in my problem, the original value here has 1, 2, 3 sig figs. My original value here has 1, 2, 3 sig figs. Technically speaking, the constant has infinite sig figs, and 303 has 3 sig figs. So that tells me that my answer must have 3 sig figs. So I'm going to draw my arrow and I'm going to count 1, 2, 3. That 0 does not round the 7 up. So my final answer here is going to be a pressure of 28.7 ATM. Now, if you were given a problem where the volume was in milliliters, you'd have to convert it to liters. If you were given a problem where the N, or the number of moles, was in grams, you would have to convert it to grams. If you were given a problem where the temperature was in degrees Celsius, you would have to convert it to Kelvin first. Okay. But this one was really nice, and we didn't do that. So you just got to plug it into the formula and chug along. Plug and chug is the technical term when we use a formula. Plug and chug. Next one. Ready, set, shall we go? Again, I'm going to take the time to identify my variables because I think that it's valuable. We have P, V, N, ideal gas law constant, which we always know, right? So that's never going to change. So that's going to be ATM, liters, mole, Kelvin. And then we have temperature, which is going to be in Kelvin. Now I'm going to go into this. I'm going to go into my problem here and try to identify what is the what values I have. This question says, what is the amount? What is the amount of Fe2 or F2 gas? So that tells me we're going to be solving for moles of F2. That's found in 0.350 liters. So that's my volume, because the L is a volume measurement. At a pressure of 0.99 ATM. ATM is a pressure measurement, and at 318 Kelvin. Kelvin is a temperature measurement. So just like we did before, I'm going to write my formula, which will be P V equals N R T. And I'm going to substitute in the values that I know in an effort to solve for what I'm looking for. So in this problem, the 0.99 ATM is my pressure. The 0.350 is my volume. The number of moles is what I'm solving for, so I'm going to leave that as its variable. R is the ideal gas law constant, which is 0.0821, and that's going to be ATM, liter, mole per moles per Kelvin. And we know the temperature here is going to be 318 Kelvin. I'm going to combine the things I can combine. So on the left-hand side of the equal sign, I'm going to take 0.99 times 0.350. And I'm going to get something in the ballpark of 0.3465. Now my unit here is going to be ATM liter. Okay. We're still solving for N, but I'm going to combine the 0.0821 and the 318 Kelvin, which will give me a value of 26.1078. Now in this instance here, the unit of Kelvin cancels out. So I'll be left with ATM, liter, mole. Now, since we're solving for N, or number of moles or amount of F2 gas in this case, we're going to divide both sides by the 26.1078. So that would look something like this. And on the right-hand side, that cancels itself out. But on the left-hand side, we're going to do a little bit of division. But hopefully what you'll be able to see here is that the units of ATM and the units of liter cancel out, and I'll be left with the unit of mole. So 0.3465 divided by the 26.1078, I get a value somewhere around 0.013271898. And again, going back and assessing significant figures, I always assess from the beginning of the problem. So I draw this arrow over here, and I see that this has 2 sig figs. This has 3 sig figs. This technically has infinite sig figs. And this has 3 sig figs. So my answer needs to have 2 sig figs. So I'm going to draw this arrow here and rewrite this to be 0.013 moles of F2 would be my N, like so. Questions? Hopefully like this isn't too bad. It's just a little bit of algebra, maybe pre-algebra even, depending where you took your algebra at. There's one more example. It is example number 3. That's going to be a you try situation. I believe in you. I have faith in you. You can do it. If you don't know where to start by identifying your variables. Start with identifying your variables. That's the first place that you want to be. Okay? Yes, sir. Yes, sir. So if you're a person who is stuck as to where to start, and I told you to identify your variables, this is what I meant. Identify what pressure, volume, number of moles, ideal gas law constant, and temperature are. That would be a great place to start. After you've taken the time to identify your variables, I would write your formula. And from there, I would start substituting my values into the ideal gas law formula. I've taken the time to substitute my values into my formula. Looks something like this. Now I'm going to simplify what I can. So in this case here, we simplified the 2.36 and the 2.75 by multiplying them together. Got 6.49 on the left-hand side. I took the 0.254 and the 0.0821. Then I got 0.0208534. Divided both sides by the 0.0208534 and got a value of 311.22, blah, 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 blah. I needed to have 3 significant figures. So my final answer here is going to be 311 Kelvin. Yes. Yes. So that's basic ideal gas law calculations. If you have any questions, make sure you let me know.